So, quick introduction here. My name's Daryl Roberts. I am the lead AI engineer, machine learning engineer at Omni AI. This is the intro to ingestion and retrieval pipelines for developers. This is very much designed with developers in mind. Not sure if you guys have seen the syllabus, but we're going to be covering topics such as vector stores, ingestion, observability during your entire pipelines, retrieval of those ingested bits, and evaluation and tuning. We're going to be touching on evaluation throughout this entire process and the things you should be thinking about when you're assembling these pipelines. But we're going to be diving into these fields much deeper in their respective sections. But keep in mind, we're going to be touching on each of these things throughout. So if you have any questions or anything dealing with what we're covering, feel free to ask. But do keep in mind, we will be covering them in much more depth in their respective sections. All right, so introduction to vector stores and embeddings. So if a model is a brainstem, then the vector store is our hippocampus. This is the shelf where all of the memories inside the model live. To better understand this, let's throw away all the AI things, all of the embeddings, the model layers, the fine-tuning, and the pre-training. Let's think for a moment about how we, as humans, think. We constantly have to recall information, past experiences, and memories. To solve puzzles, we need to think critically, consult specialists, and call in favors. AI is not some super intelligence, it's not an all-knowing central hive mind, and it's not the invention of a mad scientist. It's stateless. It has no true understanding of its own. There are emergent behaviors, and with the nature of token completion, it can mimic the image of reasoning. But at its core, it's nothing but a time series prediction model. One of the most, if not the most prominent components that take these models beyond that is its ability to simulate human cognition. Where we start to accomplish this is in the vector store. What are the memories and how do we store them? What are the experiences? Where's the critical thinking living? Its notes, its lived experiences. The experts it has to consult, its library to conduct research. Today, we'll learn how we can create and store those memories for language models. To this day, there's new and exciting state-of-the-art ways of storing and gathering that data, and new things are coming out every day. So, welcome to the Wild West. So, the vector store is essentially where all this data is being held, and we need to give the information to the model because the model has not been trained at all on current events or your own things. So, the vector store is how we cheat. We can go get whatever we need out of the vector store, give the model the answer to the question we're asking inside the same prompt, and just let it answer based on us giving it the answer and what the question. What is a vector store? So it's an optimized database specialized for storing, indexing, and querying high-dimensional vectors. So vector stores are databases with built-in nearest neighbor radar. It allows us to store semantic understanding in a separately managed database outside of our own local memory. It gives us the ability to pair semantic meaning with grounded data tags. So again, we get that semantic search that allows us to fuzzy match on words. We get to add data in context, whether it be metadata or clusters or anything like that. We're going to be touching a lot more on clustering and metadata itself in the next lesson, but I just want you guys to be aware that that does exist and that we will be covering that. And then the key applications for these are in retrieval augmented generation, which I'm assuming everybody's very familiar with at this point. It's like state-of-the-art way that people are using AI to access their own data. It grounds models in reality and informs the model of their preferences, of the user's preferences, and reminds the model what we have been talking about. All of that can be accessed through retrieval augmented generation. We can also use it for image retrieval, where we can find similar images to another image or find similar images to a string of words. This would be something like Google Lens, or imagine using it for security footage. And then there's recommendation systems, where we can use the semantic meaning of products and find other products that may lay in the same sort of semantic space. So that means that they would be a product that's closely related with the one that the customer is buying. So we're going to go deeper into the alternative memory and the metadata in the next lesson, but I want you guys to be thinking deeply as we're going through this lesson about how alternative storing could affect our vector restore retrieval and how it affects how we store these vectors inside the vector store. So embeddings themselves. Now, embeddings are essentially a numerical representation. It's a technique to represent text, images, audio as dense vectors. Because as we all know, models don't actually understand words. They understand a feeling that they've learned over the course of their training. And these feelings can be grouped with other terms that are closely related. It allows us to access contextually similar topics. LLMs don't understand language. They predict what feels most likely next or related. And embeddings are how we turn those feelings into math. It allows us to semantically capture the meaning behind words. So we're capturing relationships, such as dogs. All the different types of dogs may be in the same sort of area semantically, and cats would be all in the same area semantically. So a good representation I like to think of when it comes to embeddings and how they compress that understanding is, let's take a mystery novel, for example. If we feed an entire mystery novel to an embedding model, we hope that it's gathering all of the context clues and all of that meaning in the novel so that by the last line of that book, when it says the killer is blank, the token is, just the token is itself, is holding all of the encoding of all the prior clues we got in the novel, all the characters, what we learned about those characters, the sketchy things they've done, the red herrings that we get throughout the book. The word is essentially holding the entire compressed clue cloud. And the embedding of that word is going to be holding all the context we want in order to find out who the killer actually is. But how does it learn that meaning? What is it comparing? What's the data it's looking at to even start thinking about those things? That's when we start to think about the tokenizer and the model's actual alphabet. So let's switch over here to tokenizer. So this is essentially the way that models are viewing work. I don't want to go too in depth here because, again, you guys are developers that are going to be building with this, but I want you to understand the building blocks of how we get to the embedding model so that whenever you're feeding your own data, you actually understand how's the model considering. So on the tokenizer here, there was a very viral thing that was going around where people were saying how many R's are in the word strawberry, right? And it was kind of a hill that a lot of people were dying on when they said, AI can't actually reason, because if it could reason, whenever I asked it how many R's are in strawberry, it could just look at the word strawberry and tell me how many R's are in it, right? Well, this is how the model actually looks at the word strawberry. So we can see here, it gets split into 3 tokens. We have the ST token, and then the raw token, and berry. Now, if you think back to like the English alphabet, there are 26 letters in the alphabet, and we as humans have learned that whenever you assemble those letters in a certain order, they mean a certain thing. So let's take the word you. We know if you spell Y-O-U, it means the word you as in you're referring to someone. The model goes beyond that alphabet. It has, in its early stages, the original tokenizer had about 50,257 letters, or tokens that it took to consider. And during its training process, it's learned that whenever these tokens are assembled in certain orders, they mean certain things. So in order to understand language, it's taking those tokens and observing how they're assembled. So never in its consideration is it actually looking at the word strawberry. It's looking at these token values. Now, these tokens, whenever they're assembled in different ways, could be totally new tokens. So if we take the word strawberry and just add something simple like a space in front of it, now it's an entirely new token. And we can see that if we build up to the word strawberry, S is its own token at token 82. ST is at 302, so it has a totally new meaning to the model. STR 689, so it's a totally new token. STRA 14867, again, brand new token. And as soon as we add W, now we're falling back to ST and raw 1618. Now, in order for it to build that understanding and build that alphabet, the very first thing that happens is after the team gathers what data they want to actually train the model on, it goes through a layer of something called a byte pair encoder. So the byte pair encoder is essentially looking at all of your data, and it goes through, and its goal is to find 2 letters or 2 ASCII characters that occur next to each other often. So we have 255 ASCII characters, and then we're adding 2 tokens. This is, again, early stages. And those 2 tokens we're adding is the start token and the end token. So now we're at 257. Now, early on, the OpenAI team just said, okay, let's build up that vocabulary so that we're not having to learn relationships across only 257 characters. Let's up its vocabulary by 50,000. So in the original tokenizer, in the tick tokenizer, the very first model had a vocabulary of 50,257. There was no real justification as to why we're using 50,000. Team said, okay, well, what if we expand it by 50,000? There was no real justification behind that rather than just to see what it does and evaluate it. So to expand it by 50,000, that's how we use the byte pair encoder. So we're looking at data, and we have like an S. Let's just take the word strawberry, for example. Now, whenever we're going through all of the data and everything we scrape, let's say it's a bunch of comments on Reddit. The team is passing all of that information in, and it's looking for ASCII characters. So all of these tokens translate directly to ASCII characters somewhere in this 255 range. And on its first pass, the model may say, well, ST occurs next to each other a lot. So now ST is going to be token 258. And then we'll pass through it all again, and we'll see, okay, well, ST and R occur next to each other a lot. So now STR is token 260. And it's just going to keep doing that, where it's going through all of your data and finding letters that occur to each other, or ASCII characters that occur next to each other often enough. And once we get all the way up to the number we specified, which was 50,000 in this case, now those are our new letters in our alphabet, or new tokens. And then we're using those tokens to train the embedding model, and that's how we're going to actually understand it. Now, imagine the trade-off. Why didn't they just go to 100,000? Or better yet, why didn't they just go to 1,000,000, right? And then maybe we'd have full understanding of full words, maybe even full sentences. Well, in theory, once you get too large of a vocabulary, now you're starting to look at where those tokens are not occurring often enough for you to actually derive meaning from it. So there's a sweet spot where you want it to be large enough that you can get more unique tokens to understand, but not so large that your data is too sparse in your data set and you're not actually learning meaning. You just have a whole bunch of letters and you've only seen these two letters pair together. So now embeddings, how do they work? So let's take a look at an actual visual that I have here for the embedding models. That'll make this make a little bit more sense. So say we have a bunch of terms, for things in the royalty category: animals, tech, fruit, people, equipment, nature, and emotions. And we want to group those things or find the semantic meaning and see where they fall in our actual vector store. So we can see here, this is them grouped by their actual category. So in royalty, we have terms like ruler, monarch, duke. In animals, we have words such as tiger, horse, elephant, and so on, with equipment and tech and things like that. But if you take a look at their actual raw categories here, we can see from the equipment, the word crane, which it means some sort of like crane in equipment world, but there's also a crane in the animal world, and it looks like it's being closely related to there. And then from tech, we can see that the word mouse is being more skewed towards the animal cluster than it would be the tech cluster. And then apple, you can see, interesting enough, is being closely related to tech, but not so closely related to fruit. So if we take the model's understanding of that and actually group it here, which would be more representative of how the model sees it, we can see words like mouse are actually being grouped together with the words like animals, and apples actually being grouped with tech rather than with fruits. This is like a rough idea of what it would actually look like in your vector store if it were in 2 dimensions, but in reality it's actually in 50 dimensions, which would be very hard to fathom or understand how that looks. So similar inputs will lie near each other. Clusters tend to form topics. Examples like crane and mouse get confused. Lower dimensional models don't analyze as deeply, and we're missing surrounding context, which may reposition them. Or the training set may not have focused as much on animals or fruits. Maybe it was trained on software specifically. Having an awareness of where the embedding model is getting its information is important. What books has it read, and what sort of ideas is it more closely related to? Now we can measure these distances using math. So because we understand the meaning, even when the passage is only one word, So let's take a look here. We have something, this is a very famous example. So if you take the word king and take away the word man from king and add the word woman, you would imagine that that's essentially what a queen is. So king minus man plus woman equals queen. So in the vector space, we would hope that if we took away the embeddings of king and took away the embeddings of man, and then added the embedding vector of woman, then the new embedding vector should be somewhere close to the word queen. So here we just use a wave2vec, which is a static embedding model. We'll go more into the individual models later, but this is mostly for the visualization. And we're going to go ahead and get the embeddings for the word king and embeddings for the word man, embeddings for the word woman, and embeddings for the word queen. And we're just going to take the king vector and reduce it by the man vector. And then that new vector, we're going to add the woman vector to it. And let's see where it sits. So we can see in this 3D representation here, words like son are close to the word father, and king is close to prince. Same with queen and princess, woman, girl, daughter, mother, because they're similar topics. Now we can see here, if we take the word king and reduce it by the vector of man, it's sitting over here. And then if we add the woman vector, we can see now it is positioned pretty firmly in the same area as the queen vector, which is exactly what we want from our embedding model. This tells us that it does understand the meaning of these things, not just the vectors themselves, but those vectors are actually representing the meaning. Then, with something like a cosine search, we can actually measure the distances. So that line we see, we can actually measure how far away is it. So we're just going to take a really simple model. This is the all mini LM L6. So the glove model was 50 dimensions. The glove 100 was 100 dimensions. This all mini LM is still a fairly small model. It's at 384 dimensions. So we're going a little bit more molecular now. And if we take a look at the words dog and puppy, we can see they're about 80.4% similar. And then if we take cat and feline, we can see they're about 69.7% familiar. And we can do that with pretty much anything. So let's see how far away is cat and dog. It looks like 66% similar. Must be that sentence transformers, trained on animals or pets, and they would group these in the same. All right, so embedding dimensions. We kind of talked about this when we were talking about Glove 50 versus OpenAI's versus the others. So the embedding dimensions just are essentially how molecular do we understand the language. So vector dimensionality is like camera resolution. More pixels can reveal finer detail, but the file gets heavier. And using the wrong model for the job is like shooting that image with a blurry lens. So you may get a 4K shot, but you end up with a blurry 4K image. So you have small models such as Glove. If you're going to 50 to 300 dimensions or under 512, that's a very small model. You're looking at models that can process very quickly. They're small enough to often fit on mobile devices like a phone, but their downside is that they miss nuance. So the word bank, if it's talking about like a river bank or a financial institution bank, the nuance between that language may fall apart. Then you have transformer-based models. Those are more in the range of 768 dimensions to 2000 dimensions. This is where things like BERT and OpenAI come from with the new transformer-based understanding with the attention mechanism. This is the nice sweet spot when you're approaching RAG or semantic search in any sort of way. This is a good place to start. It gets that sweet spot where you have the understanding of the language, but you also are not so large that it's over computationally expensive to search. So these are where you start to capture polysemy, which is a really fancy word for saying a single word can have multiple meanings, like the word bark or the word bank. And it's still comparatively fast to index. Not as fast as the small models, but much faster than these large models. Then in the large models, we have things like text embedding 3 large, which is OpenAI's large embedding model. There's also fine-grained, fine-tuned models on Hugging Face that we'll explore. This is where you start to get really, really large understanding of the data, and you start to get these specially fine-tuned embedding models. So the general trade-off for using a large model is you may be looking at about 4 times more RAM use, a slower search, and it's more susceptible to overfitting. If you imagine you want to analyze more features, you essentially need more data. And if you're not giving more data, then really what you're doing is overfitting to your specific data set if you're going to be really, really analyzing it at that small of a molecular level. Now, at cost, if you take 1 billion rows at 768 vector size, you'd be looking at about 3 terabytes of storage. If you take that same 1 billion rows and up it to the 3000 dimensions, like with a text embedding large, you're upping that storage to 11 terabytes. A general rule of thumb when you're choosing an embedding model like this for speed, for inference speed, is that every time you double the dimensions, you're increasing the speed, or you're decreasing the speed that it can search your vector store by about 1.7 times. So we also have the idea of curse of dimensionality, which is expressly mentioned in a Yin and Chin paper named On the Dimensionality of Word Embeddings. That study showed that often accuracy plateaus despite growing dimensionality. So your goal as a developer is to go as small as possible, but still have a good accuracy trade-off. So you want to find the smallest possible model that gives you accurate results. That way you're optimizing for inference speed, but also optimizing for accuracy. So if you have mobile or real-time requirements, often go for those small models. If you just have general RAG and you're developing chatbots, then start looking at that transformer-based model, no larger than 2000 dimensions. But if you have a specialist domain, such as legal or code or anything like that, then you can go to those large models that have a more molecular understanding. If you're not sure where to start, my best advice I can give you is start with a transformer-based model. Start with that medium ground, measure your hit rate, your recall, which we'll be touching more on later, but measure your actual metrics on your data, and then start changing things. Don't add complexity for complexity's sake. Start small, figure out how it's performing on your data, and then iterate from there. Right, so embedding models overview. So we've kind of touched on the training and how that works, and by using that training, we are building a reference space. And then we can map new sentences coming into the embedding model to that reference space, and the geometry in that reference space encodes meaning. Now imagine you take a base embedding model like text embedding small from OpenAI. That would be like someone came to your country and learned your language. They have a grade school understanding of vocabulary, and they just understand generally whenever words occur next to each other, they have certain meaning. Now, a domain-tuned embedding model on something like legal or medical is like sending that general model to college. So now it has a law degree and it has a much better understanding of like subsections and laws and legal talk that may happen in that space. It has a way better understanding of how those words affect other. So I do want to touch a little bit on the embedding model and like how it's trained. So here we have a good representation of an encoder. An encoder is just this left section here, which is what BERT is. So it's input of like how the actual embedding model is trained. So imagine now we've turned words into tokens, and we understand that those are our letters and how we're building words. So first, those tokens go into an input embedding, which is just a static embedding. So every time the word "the" comes into the encoder, it has the exact same embedding as every other "the" that comes into this model. Then we add some sort of positional understanding. So let's go to this here. So we just take the sentence like the cat ran. We adding a positional encoding, so "the" in the first position is going to have a whole new meaning than "the" in the second position or in the third position. And then "cat" in the second position is going to have a whole new meaning than "cat" in the first position or third position. And same thing with the word "ran." So we're adding some positional knowledge of where these words are occurring in the sentence to the model. Then after that, it passes to a multi-head attention. We could talk for hours about the multi-head attention, and I really recommend if you want to do a deep dive, read that 2021 paper, Attention is All You Need. But what I really want you to take away from this is essentially what the multi-head attention mechanism is doing is understanding how to really, really understand language. So every single word after it's been positionally encoded and encoded just because that's what the word is, every word gets a query, a key, and a value. So essentially every single word has a query, and what the query you can imagine is what types of words affect me. So what types of words am I looking for in this sentence that are going to change what I mean? So it may be looking for, maybe it's looking for the word cat, or it's looking for the word ran. It's looking for certain words that represent themselves in a certain vector space. The value is how these words are found. So the cat's like, this is me, this is what I look like. So the, using its query, can find the word cat. Then you have the key. And what the key is, every word has a key, and it says, okay, once another word has found me using its query, the key is, how do I change with that word? Like, what's the value that I provide to that word and how I change it? And that's what the key represents. So we've learned that words going in certain orders may mean certain different things, and we know that it's looking for certain words to change it, and all the words have ways that they change other words. Coming out of the multi-head attention, that looks like an understanding of language. Even though it might not be, it's how the model's able to represent those things numerically. Okay. And then it just goes to feed forward, where the model's going to analyze those things and then output a compression of understanding. So if you imagine, words come out and it's looking at all of the words going forward, because you're inputting an entire sentence. So whatever you're saying to ChatGPT in your language, it can look at all of your language going forward, and it's going to look at all of your language going backwards. That's what the B in BERT stands for, bidirectional. So it's looking, the word ran is looking at both the words cat and the, and it's changing the word ran. But also the is looking at the words cat and ran and seeing how it changes it. So outside of that encoder, what you're actually getting is an understanding of language, front to back, back to front, a full understanding or a mimic of understanding. And that is essentially how the embedding model is trained. Now, here's the part that's the most important. Let's go in and start selecting what embedding model we're going to think about using. So the first thing you need to consider is, what's my data type? Am I going to be searching or indexing over text? Am I considering images, audio? Are we doing entire documents, or are we just doing sub-documents? What's the throughput requirements? What's the speed that I need for my model? What's the type of use case? Do I need it to be instantaneous, or am I okay with waiting a couple minutes to get a good answer? What's the cost of inference? How many calculations does it have to do? How much RAM am I using? Dimensionality, is it too wide? Is it too small? And the task, what is the actual problem that we're trying to solve? So let's go over to the MTEB leaderboard, which is the leading board on Hugging Face for embedding models. And we can see here that on the MTEB leaderboard, all the embedding models are separated for different functions. So if you have an image to text model, where you're going to be searching for images using text, these would be your best bets. And you can see that they're ranked with the best performing all the way to the least. And all of these are running on their own benchmark. So let's look at performance per task. And we can see that all of these here are particular benchmarks that this model's been tested on. So each benchmark has a totally different job. Like, one may be, how good is it at answering questions using images, when another may be, how good is it at captioning images? How good are we at matching images with certain things? Because remember, our embedding model is an understanding of language, and it's been fine-tuned to understand that language. But how it's been fine-tuned and how it performs on certain tasks actually informs us what embedding model we want to use. And then the same thing with code. We can see we have embedding models ranked, and then what tasks they're good at. And then same thing with legal. We have the models themselves ranked and what tasks they're good at. Now, depending on your task, you may want to research what benchmarks are best performing. I do have a quick little cheat sheet here that I'm going to be giving you guys. These are just the most common benchmarks for different tasks. So for like code-centric, the code search net retrieval benchmark measures how well we can represent natural language with code and search across GitHub with languages. This is a bread and butter test of how well an embedding aligns with doc strings and queries to a source. But then we also have something like a Stack Overflow QA, which retrieves an accepted answer to some sort of troubleshooting. So this is you're looking for troubleshooting advice for a certain issue. This embedding model that performs well on this benchmark may be the best for that job. And then same thing with legal. We have some that are specialized in civil law retrieval, some that are multiple choice QA over legislation. And then same thing with medical. They have their own benchmarks that measure particular tasks. And then with image to text, we can see same thing. We're representing data in a certain way for a certain task. Now, I do want to caution you guys. because this space is moving fast and everybody wants to be an industry leader. And in order to become this, we kind of talked about the overfitting before. But what a lot of these companies are doing is these are these benchmarks that are heavily tested, and that's what gets you ranked up with Hugging Face and recognized. But what a lot of people are doing now that their weights and things have been open sourced, people are finding that companies are directly training on these benchmarks. So they're training exactly to perform well on a specific benchmark, so that way they kind of inflate their own use. There's not a real way to understand what companies are doing that other than maybe reviewing the model and looking at the research that was done on that model. The best thing I can say to do as a developer is pull down the models that you say would be the most useful by recognizing what benchmark tasks most closely match your use case, but also just using the model in production or during your development and measuring how well it does with your task. Is it retrieving the chunks that you need? Is it actually embedding the chunks correctly, putting things and understanding things in the right spaces? If so, then great. If not, then it may be a sign that the company just overfit and inflated their statistics using that benchmark, and it's not actually performing well in the wild on that benchmark, just on the benchmark. Now, in order to really understand sort of what these models are doing and what's coming out the other end, we did kind of touch on how the BERT is working as far as understanding language front to back and back to front. So in order to better kind of show this, I put together a quick demo on ResNet. So ResNet is essentially a image classification model that it takes in an image and it can say exactly what that image is or the probability of what that image is. So if we take something like this dog picture, which is here, this cute little guy, and we feed it over to ResNet, what it's going to do is analyze that image and try and give you back a percentage chance that it belongs to a certain class. So we can see coming out of ResNet, it's saying that there's a 90.3% chance that it's a Blenheim Spaniel, but you can see there's also other dogs that kind of came to the top of the list, like Welsh Springer, Cocker Spaniel, Sussex Spaniel, that have very small chances. But ResNet has thousands of classes. I'm just showing the top 100 here, but you can see it has been trained on all kinds of different classes. It knows the difference between a llama and a quilt. It knows the difference between an Irish Terrier and a Norfolk Terrier. It knows, the difference between bubble and umbrella. So it's been trained to really analyze an image and tell you what the difference is between these things so that it can give you a prediction of what that thing is. Now, if we take a look at the actual infrastructure of ResNet, we can see it's a deep learning model that has tons and tons and tons of layers. And I'm not going to go into detail of like what these layers are. You can see that there's convolutional layers, which I kind of mentioned earlier, for analyzing images, and normalization layers for generalizing and things like that. But this is where the actual magic happens. So this very last dense layer, you can imagine, is an exact replica of the number of classifications it has. So let's say ResNet can tell you the difference between 1,000 specific objects, and you can make a guess out of those 1,000 objects, what is it? So this dense layer would be 1,000 vectors long, where every single item in that vector is a probability that it is a certain class. Now, if we rip that head off, this dense head off, and we leave it at this layer here, or this convolutional block is the very last time it is analyzed, in order to get this dense vector, it's going to look at this layer here. And what this layer is, it's a compression of all of the analysis that it's done. It's a feature matrix of what are the features on this image that give us an idea of what this thing is. This is the black box nature of the actual machine learning models, because we don't actually know what are the features it's caring about. We can assume, like if it's looking at a picture of a dog, we know that maybe it's considering how floppy are the ears, how long is the snout, does the tail wag when it's happy, things like that, right? So by the end here, we have an entirely, X number feature matrix that represents all of the things that we've analyzed throughout the entire model. And this dense layer is going to look at that feature matrix and say, considering these features that I've analyzed, what is the percentage that it is this thing? So if we rip this head off, essentially what we're left with is a 2048 vector of all of the features that it's analyzed. So this is what the embedding model actually is. So if we revisit kind of BERT, the data coming in is going to be like the cat ran, And BERT is going to randomly remove tokens. So like the cat would be gone and this would just be a blank. And what BERT is trained to do is look at the word the and look at the word ran and give us on the output some sort of probability. So this is that 50,257 tokens. The very last dense layer is going to be 50,257 items long, and every single item in that vector represents a different token. And it's going to output a percentage chance that this token is one of those. Now, so with machine learning, we saw with ResNet how it compares to BERT, and we can kind of imagine all embedding models are this way. They are some classification model that has been trained a certain way to classify something, and then we can rip the head off, and that is how we get our compressed features. So during this grind, the layers learn to compress those meaningful features and give them back to us. For a classifier head is just essentially a thin label translator. It's looking at those features and saying, okay, considering these features, what's the likelihood that it is this thing? And regardless of modality, text, image, or audio, the last hidden layer of that model is a memory snapshot of what the features are. So for text, we have models like Word2Vec. Word2Vec is a static model. All that means is it's looked at thousands of points of data, and instead of saying, okay, because the word bank occurred after the word river, it means something different than when we're talking about financial bank. It's just looked at all of this data and it's trained for speed. So it's saying, okay, well, bank could be talking about a river bank, and it also could be talking about a financial bank. So it's going to find the average between those two embeddings and position the word there. It's static. So it's not going to be doing any live calculation or live understanding of the language. It just, every single word is mapped to an embedding vector that it learned over the course of its training. Glove is a very small model that we kind of talked about that understands text on a smaller level. Then we have BERT, OpenAI's Text Embedding 3 model. These are all sort of models that understand text. Then for documents, we have things like Doc2Vec and SentenceBERT. I also want to give a shout out to Snowflake. They all kind of have learned to split their embedding models into two parts. You want to represent the data coming in, all the documents coming in, differently than you want to represent the queries to go fetch those documents, right? So we've learned that documents need to be represented in the embedding space a certain way inside your vector store, but if you want to go fetch those documents, your query needs to be embedded a certain way to match those documents more closely. Because if you imagine a document may be an answer to something, but a query coming in is a question to that thing. So those representations may not be one-to-one, and that's exactly what these document embeddings aim to minimize. Then you have images such as clip, which we kind of talked about, that comes with image and text. So it can reference text as it comes to images. So the word dog would be closely related to images of dogs. And then you have ResNet, which is just image to image. So it's specially trained on if you give it a picture of a dog, it will return another picture of a dog inside your vector store. And Lava is very much the same way. Then for audio, we have Wave2Vec and VGG-ISH. Audio can be represented a couple different ways. There are embedding models that take straight spectrograms, which is just the actual representation of the audio itself, and translates those to embeddings. But you also have audio models that will take your spectrogram and put an in-between step where it adds tokens, and those tokens are just the phonetic alphabet. So it takes that wave, compares it to the phonetic alphabet, and then it embeds the phonetic alphabet as tokens instead. Do you have any questions on embedding model examples by modality or anything like that? Okay. Semantic, similarity, and vector stores. So this is where we start to actually use our embeddings that are stored in the vector store. So given the word puppy, you want to find passages about small canines, or with cats, you want to find passages about felines. Who's ever dug through their email and you wanted to find a particular email, but you didn't remember exactly what was said in that email? You just remember it was something about a meeting at a certain time, and you didn't save it to your calendar, so now you have to go find that email, and you have to use keywords to find it. The embedding model is trying to be that middleman. So instead of saying, searching the word meeting in your email and sifting through 1,000 emails that have the word meeting in it, you just tell the embedding model, I'm looking for an email that said something about this, and then you get the exact email back. That's what a semantic search is. So let's go over the actual distance metrics, which we kind of talked about earlier with the cosine, dot product, and Euclidean, but let's look at actual images of that. So I'm going to go ahead and pull up this gentle introduction to vector databases by Weaviate. They did a really good visual on the actual measurements. So here we have what we talked about with Euclidean or L2 distance, which is just the raw distance between two metrics. You can imagine this is how far away is the vector. We'll circle back to Euclidean after we kind of talk about cosine. So cosine is your difference between the vectors in the vector space. So let's imagine we have the word baguette and Eiffel Tower. The distances here would essentially be how French is the word, right? And if we're saying Euclidean distance measurement, we're just saying, okay, you know, what's the difference between these two vectors? We know that they're in the same space. They're both French things, but how French is it? This would be like your volume, like how deep is it into this vector space. Cosine similarity doesn't care about how French it is. It'll just go get both baguette and Eiffel Tower because they're both French. This just measures how, you know, how French is, or this is how French is it. This is just, is it French at all? Which often, you know, we may be using this because we don't care, you know, how deep it is in that vector space, because especially if we don't understand it, cosine similarity would be better in that case. Then we have dot product, which considers both the vector angle and also the distance. So we're just taking that dot product and finding how French is it, but also is it French? And we're kind of weighting those results for us. We have L1 distance. I wanted you guys to be aware that this is out there, but almost no vector store is supporting this, and it's not very used. It's very rare that you would need to do L1 distance. I just wanted you to kind of be aware of it. This would be like a block, like you need to go all the way to the side and then how much up you need to go to actually match this vector. To know which one to use, you need to do research on how the embedding model was actually trained. Like OpenAI's ADA002 was optimized for cosine similarity, but MiniLM was optimized for cosine, dot product, and Euclidean distance. So if you choose an embedding model, you need to look up how was it trained in its vector search. Is it trained on L2 or cosine? Because if you just pick one and it was trained on L2, but your pipeline is measuring cosine, you're not going to get great results. Question for the class, is semantic similarity the only way to store things in a vector store? That's right, I see a thumbs down. No, it is not. So yeah, so we have more ways. So semantic search is just one of the key ways that we can do this. We can compare what certain words feel like with other words that have already been stored and how those things feel. But we also have things like keyword search, where we can look for specific words. We have metadata searching and all of those things, which we'll touch more on in the next lesson. But I do want you guys to be thinking about semantic similarity isn't the only way to do this, but it is a very popular way to do it, and it's a good way to search your vector store once you've eliminated outliers. Data in context. One of the biggest issues in a vector store is it needs to be sorted very quickly. You need to go get your data fast. There are tricks like indexing and clustering and metadata that allow you to do this. So going beyond semantic search, if you were to semantic search every time all of your things, imagine how slow that would be. You have to do a calculation across every single row. And if you say have information about fruit and information about animals, and somebody asks a question about an animal, why would you do calculations on all of your fruit chunks if you're looking for an animal chunk, right? So finding ways to optimize that are key when it comes to your vector store. Now, clustering. We're going to go really, really deep in clustering on Thursday in our next session, but it is important to understand what it is when we're selecting a vector store, because different index techniques use different clustering. Yeah, so clustering is an unsupervised algorithm. So if we look at our demo here, this would be, oops. Let's go back to lesson 1. So clustering would be like here, what we saw here. So each cluster is kind of like its own meaning. It is just an unsupervised way to do these things. So let's say you get documents in and you're not sure what the documents are about or like the different topics that they span. Clustering is a good way to just organize those documents in a way and understand what is the partition, what's the difference between these chunks. It helps us to organize and explore and summarize large data sets. If we're coming into this and have no idea what types of topics are inside of our data, we may not have a way to actually tag it and understand that data. We just hope that an unsupervised method like clustering can draw those conclusions for us. It can improve retrieval quality and efficiency in a vector search system. And just a few common techniques are k-means, spectral clustering, GMM, and density-based. We're going to be covering these in great depth in the next section, so I don't want you to get too wrapped up in the specifics, but just that clustering is a way that we can group similar vectors close to each other. So if we imagine clustering sort of like as a SQL query, we would say select all the chunks that are close to this embedding vector, where the cluster ID equals 7, for example. And we've already minimized the amount of data that we're searching. It increases your speed. The clusters themselves give us sort of a summary of all of the chunks that are inside that cluster. And it allows us to explore our data by seeing how the model is clustering these things. We can see what types of things is it actually paying attention to. If we see a lot of the same words appearing in the clusters, we know it's paying more attention to the words themselves. If we see like certain concepts being clustered together, we know that it's focusing on the concept differences. Different vector stores support different types of search. Again, we're going to be touching more on these actual search methods during the retrieval class, but I want to give you a high-level understanding because in order to choose your vector store, you need to understand what it actually supports for you. So a dense search would be your straight-up semantic search. You have your documents embedded and sitting in your vector store, and then you have an incoming query that you're then going to embed. Then you're going to do a calculation across your entire vector store with your query embedding and see, okay, which of the chunks inside my vector store are closely related to this vector. So it's a very resource intensive and could take a long time. But it has the highest of all accuracy or conceptual recall. Because you're making a measurement to every single chunk, you can be very sure that the only chunks you're getting back are the ones that are closely related to your query. Sparse search is a keyword search. So if you're looking for passages about cars and you bring up the car word in your query, you're going to find chunks that have the word car in it. They have, very fast indexing because the words are there and you're just basically looking for keywords inside that passage. But there's no semantic understanding. So if the chunk that would answer your question actually has the word automobile in it instead of car, you're not going to find that chunk, and you may not get the correct answer to your question. Hybrid search is sort of the best of both worlds. It's going to combine dense and sparse search together to sort of optimize speed, but also not trade so much accuracy. So there's two hybrid search methods that are the most common. There's the two-pass, and then there's the weighted. So two-pass is essentially we do one search to our vector store and give back the top, say, 50 results. So if your vector store is 10,000 lines or 10,000 rows of documents, the sparse search will go get you the top 50 that match that query, and then we'll do a dense search on that top 50 and just choose which of those 50 are the top 5, now searching for dense. So instead of doing dense search over 10,000 rows, we're only doing it over 50. A weighted search will do the sparse search and the dense search, but at the same time. So by doing the sparse search calculations, we're ruling out chunks that the dense search should not check. And then by doing our dense search calculations, we're ruling out chunks that the sparse search should not check. And if we give it some sort of weight, saying that sparse search gives about 30% of the vote and dense search gets about 70% of the vote, we then can understand between those two scores which chunks are the highest relevance, say like the top 5. Now, all of this was culminating so you can understand the indexing methods inside of vector stores. So the things inside your vector stores you need to be considering are, what are the dimensions that it can hold? What's the speed? How is it clustering these things? What types of search does it represent? And also these indexing methods. What indexing methods are supported? So these are the 3 most common indexing methods that most vector stores support, and you're likely going to be choosing one of these 3 whenever you're approaching your own solution. So flat indexing is just what it sounds like. It's essentially just your table as is, and you're going to be searching across every single row for what vector most similarly matches. It's very much related to like dense search. So if you're doing a dense search on a flat index, that is literally meaning that you're going to check every single row. This would be like every book in your data store is on one shelf, and you're going to go through and read every single spine until you find the book that matches what you're looking for. There's no pre-processing needed in order to store here. You just can store your indexes or your embeddings directly. But again, you're going to be searching every single row. You're going to have the most accuracy at this method because, again, you're searching every row, and by doing so, you're not ruling out any data. But timing is going to be heavily affected, your inference speed. IVF, I kind of want to represent in a drawing. So IVF is doing that clustering method that we kind of talked about. So you get clusters of your data that IVF has been already trained to do for you. And a query comes in, and that query could sit in this cluster. And inside this cluster, all these clusters are a bunch of your embeddings that you've already stored. Now, if your query comes into this vector here, we can just rule out these clusters altogether. We're not going to search any of those. We're just going to search all of the rows that are inside this cluster here. But if your query comes in somewhere like here, we're only going to be able to rule out these two clusters because both of these clusters need to be considered for that query. And then same thing, if it kind of falls in the middle, now you need to kind of do that brute force where you're searching all of these vectors. So IVF is just essentially managing your clusters for you and finding where your query sits and then deciding for you what clusters need to be considered. And it greatly increases your time because you're not searching every row. You're only searching the rows that fall inside that cluster. Then we also have the most common method, or the most widely used, which is HNSW. It's hierarchical navigable small world indexing. This is a graph-based approximation of nearest neighbor. So if flat brute force is looking at every single spine on the bookshelf to find your stuff, and IVF is like you're looking at a mall, a map of a mall, you're finding what wing the store you're looking for is in, and then you start looking at all the stores in that wing. HNSW is like your social networking hop. So let's say you hurt your ankle, and you have a friend that you go talk to, and that friend says, oh, okay, well, I have a doctor friend. And then you go to that doctor friend, and the doctor friend says, yeah, I'm a doctor, but you need to see a leg specialist. So then you go to a leg specialist, and that leg specialist says, yeah, I'm certified on legs, but ankles aren't my strong suit, and then he recommends you to somebody else. That's exactly what the HNSW is doing. So if we imagine here, we have all of our vectors sort of in the space, and all of these vectors create a graph whenever you insert the documents. So each of these vectors are connected to other vectors. And those nodes or those edges are drawn by just how closely related are they. So let's imagine this more flat for a better understanding. So the outside of that graph are vectors that are very sparsely connected. So these are the ones that, maybe it only has one or two connections, maybe, three to other vectors. So they are connected to other ones inside that graph. Now your query comes in, and it's immediately going to start on the sparsest layer of that graph. So it's going to find which of these embedding nodes are the least connected to other embedding nodes. And each of these have their own embedding vector. And your query is going to say, okay, which of these am I most closely related to? And it's going to say, okay, I'm the most closely related to this one here. So now everything that these are going to is instantly taken away. So now we can go here and say, okay, now of all of these that this one's connected to, which am I most closely related to? And it may be this one. And then that one's also connected to more nodes. And you're just going to continuously walk down that graph until, say, you get here, and these nodes are so far away from your query that we discover we can stop here. So it's going to do this greedy walk every time, and it's basically just getting rid of large amounts of data to not search over. It's only searching over ones that are relevant and are being recommended by essentially other vectors. And once it gets to the spot where it is more deviated from the vector by going deeper, then that tells us to stop. Stop where we are and grab the, say, 5 most closely related vectors that are close to the node that we...
Cool.
All right. So in selecting a vector store, we have options such as PGVector, Pinecone, Weaviate, and Phize. So in Postgres, it feels like Postgres, but it's a new data type. Its pros are you have SQL filters that you can use. So as developers, you've probably used SQL, a million times. You're very familiar with how SQL works and how to form your own SQL queries. But the downside is it is not optimized for tons of dimensionality. So once you hit that 3K dimensions, which would be like those large models, it starts doing something called half vec, which it's trying to compress those 3,000 features to a smaller vector space. So you're going to lose a small amount of accuracy once you hit above 3,000 dimensions, but below that, it is excellent. You get that SQL knowledge, you can use joins, metadata filtering, and all of those where clauses. Super simple. All major cloud providers have an already managed database solution for PGVector, and with your extensions, you can add the vector class to it. So if you already have, that SQL familiarity and you're already hosting a Postgres database for, other clients, why pay for a whole new solution if you can do everything you need in one single solution? Then you have Pinecone, which is a software as a service. You have zero database management you need to do. It will auto scale for you to billions of vectors. It has that built-in HNSW, just like PGVector has the HNSW, IVF, and support for all of those things. Pinecone has those same supports. Also, out of the box, Pinecone supports hybrid search and sparse search, whereas PGVector does not support hybrid search or sparse search out of the box. But for Pinecone, you're going to be paying a cost per pod and per lookup, and you're locked into their ecosystem and their API. It's very difficult to take your data out of Pinecone and move it to something else if you want to get away from their system. Weaviate is another specific software built for vector stores. The pro is it's actually open source. It comes with very good sparse search and hybrid search right out of the box. It also comes with GraphQL, which is another query language where we can use things like near text or near vector instead of the where clauses that we would use in PGVector. Downside is it ships all of its deployments in Kubernetes. It's great for reliability and rolling upgrades, but it means that you or your DevOps team must already run a Kubernetes cluster and be comfortable with Kubernetes and YAML. Be comfortable with the resource quotas and persistent volume claims. If your stack or your current technology stack is consisting of Docker Compose or a single EC2 instance, spinning up Weaviate is significantly more difficult than just running a Docker run for PGVector or create pod on Pinecone. It's also written in Go, so it runs fast as a microservice, and you gain those features out of the box, but you'll have to monitor multiple Go services, expose GraphQL, and manage the updates yourself. So there's more operational overhead with Weaviate, but you do get a lot of really cool features right out of the box. And then Phize is Facebook's vector database management system. It is extremely optimized for dense search. It has no support for sparse or hybrid. The entire purpose of Phize was to make dense search as fast as possible. So it's GPU optimized, compression of features, really good C++ indices. It has the fastest HNSW and the fastest IVF lookup. Just in general, if you're doing only dense search, Phize is going to be your absolute fastest solution, but you don't get any sort of sparse search or metadata filtering or anything like that. You would have to be comfortable enough with your code to be able to build in those other solutions before going to your Phize index. All right, so this criteria in selecting your vector store provider is going to be, how do you need to host it? Are you going local? Are you going to the cloud? What's the cost structure? How much is it going to cost me to use this vector store continuously? Integration, how difficult is it going to be to integrate into my current ecosystem, and how much work am I going to have to do to maintain it? And then scaling needs. What does my end product look like? Do I need, is needing over 3,000 vectors essential for my use case, or will under 3,000 vectors do the job? How many rows of data do I plan on using? Just what's the scale of my final product? My solution or my recommendation is to often start with PGVector because you can host it locally in its own Docker container. It's easy to prototype. It's great at indexing, and you can represent those vectors under the 3,000, which at the start we're most likely going to be doing, and it does well at handling data at large volumes, and you get that SQL muscle. So my recommendation, start with the PGVector, something simple that's easy to understand and that you have experience with, rather than learning an entirely new system and getting that overhead of having to manage a new system. Now, not to beat a dead horse, but here's why we chose PGVector. So we get that native PostgreSQL knowledge and use case. We measured our cost, the integration, the scale, and everything that we needed or needed access to, PGVector supplied. Yes, it doesn't get the sparse search or the hybrid search out of the box, but there is a extension that you can add called PGTRGM, which gives you access to that sparse vector data type, where you can host all of your dense embeddings right next to your sparse indexing, all in the same table. You get those SQL superpowers. You can join vector similarity with JSON searches with your metadata. You don't have to do double hops or round trips across multiple providers in order to do so. You can create SQL queries using the where clause, the and clauses for certain metadata filters. The whole idea of it is, why bolt a new engine to a car when we can turbocharge the one we already know? Cost and performance. So benchmarking on PGVector versus something like Pinecone, it was actually found that PGVector is about 28 times faster than Pinecone, and it costs about 16 times less. The filtering gap is closed. So it used to be saying, if you want to use a vector store, use a solution that was specifically meant to be a vector store, and that used to be the justification, like always go to Pinecone, always go to Weaviate. That's no longer the case. PGVector has open sourced everything and how they're handling the storage of vectors, and they're using something called streaming disk ANN. It's not to go too deep into that. It's just a way that we can very quickly stream over rows of data and do those vector searches. And this is the exact same trick that Pinecone has been marketing as to why they're so fast. So we're using the exact same indexing method and speed that Pinecone's using, but for a very small fraction of the cost. And across dedicated other vector stores, Postgres was seen with the exact same vectors to only lose about 1% recall. So you're getting all of this extra functionality with only trading away about 1% accuracy. Now, if our vectors do outgrow that 3,000 dimensions and we start going to half-vec, and that half-vec is giving us poor recall on our chunks and finding the data in our vector store, then maybe Pinecone or Weaviate go back on the table, and we need to reconsider what vector store we're using. So if your team is already running Postgres, why pay twice? Why not just use PGVector? If you don't, what's your projected scale curve? How robust does your app need to be? How fast are you scaling it? How many documents are going into it? And what's the vector space that we're going to be covering? So after you've chosen your store, we're going to be thinking about, okay, now let's start ingesting data into this store. And that's where we're going to start kind of going into the ingestion module. But the vector store itself is going to be the backbone of everything we do. All right, guys. So let's just recap this lesson. So we've covered what a vector store is, what are embeddings, and how do models create understanding of our language. And by understanding how it understands our language, we now can understand, okay, this is how it stores in a vector store, and this is how we're actually indexing on it. We also covered semantic similarity. We got a brief overview of clustering, indexing, what vector stores support certain methods of indexing and clustering, and the vector store products themselves.